Okay, so we've covered a lot of different integration methods, and they basically revolve around finding some sort of antiderivative. Like, like one of the things that we started with was this idea that every derivative rule can be rewritten as an antiderivative rule, right? To be able to use the fundamental theorem of calculus. And then we talked about other things like U substitution, what else? Like trigonometric substitution, trigonometric integrals, all these other techniques basically to find some sort of way to find the or integration by parts, right? The list was pretty huge, right? There's all these things you can do to find these antiderivatives, and then use the fundamental theorem of calculus to like solve your definite integral. Okay, that's not always gonna happen, is the shitty thing. Okay, so when that doesn't happen, you basically have to use numerical methods. So if you remember, how did we originally calculate stuff in a definite integral? What we did was we set up the limit of a Riemann sum, right? So the Riemann sum is based on this idea that you're adding up the areas of rectangles, right? You have this partition, which is each delta x wide. You find a bunch of points, you plug in the function, you get these rectangles, you add them together. If you take the limit, you get the exact answer. If you want to estimate it, you can just add up the rectangles. So the question becomes, well, if you can't take the limit of your Riemann sum, are there other shapes, or are there other things that you can do to make your estimate more accurate? Okay, so instead of looking at summing rectangles, eventually we're going to get to summing these other shapes. Does that sound good so far? Like, that's the whole idea of what we're going to talk about here. Like, if you needed to use a computer to calculate everything, what would you do? Okay, so that's what we are going to focus on today. So let me go into writing mode. Okay, wrong picture, my bad. There we go. Okay, so let's draw what we've got. Boom. Let's say you have some function, f of x. Okay, and you want to find the area from A to B. Okay, so I'm going to sort of re-summarize here what we've talked about. If you wanted to find this definite integral, we have A to B, f of x dx, and that's defined to be the limit as n goes to infinity of this sum I equals 1 to n of f of xi delta x. Oh shoot, yeah, let me record it. There you go. So this is what it's defined to be, and then to remind you, right, this f of xi times delta x, that's the area of an individual estimated rectangle. Area of individual rectangle. And then remember, we have this formula for xi, which is a plus delta xi, correct? And then delta x is equal to b minus a over n. So remember, the xi's are the partition, right? They're the left and the right endpoints. So if we go and we draw some, right, this first one right here, a is always x0, so we can write x0, x1, x2. I'll just like draw a couple of them in there, x3, x4, and then in this case, my b will be x5. So you can imagine, right, like a partition with 5 rectangles. So remember, we use the word partition to mean we're splitting up the interval from A to B to find the points which determine the height. Okay? Now, we've talked about in the past, like depending upon whether you're doing a left endpoint or a right endpoint approximation, you would start either from 0 to n minus 1 for the sum, or if you wanted to do the right endpoint, you would start at 1 and go to n. Okay, now there's actually another option here that we're going to discuss now. Instead of the left or right endpoint, we're going to do the midpoint approximation. So the midpoint approximation's a little annoying, because instead of evaluating the height at x0 or x1, we're going to evaluate the height at the midpoint of them. So you get these other 1, 2, 3, 4, 5 green points that will give you the height. Okay. So instead of calling that xi, I think the book calls it xm, or they call it mi. So mi is the midpoint. So, like for instance, this m1, actually do we start at 1 or we start at 0? We start at 1. So the first midpoint is the average of x0 and x1. Okay, this first point right here, where you determine the height, it's the middle of x0 and x1, so it's the midpoint. The second midpoint is going to be the average of x1 and x2, and so on. So you would like go and you draw it, and then you get this. Okay, so you'd get the first one, which would look like this. Second one which would look like this. Now this is different than the left and the right endpoints because the height's determined by the middle. So notice if you want mi, you can look at this. You can see like m1. You see how it agrees with this one over here? Okay, so your mi is going to be equal to xi minus 1 plus xi over 2. Again, remember how I've talked about I never memorize where the sums start for the left or the right endpoint. I just draw the picture each time. I do the same thing for this. I never remember. If you were to ask me randomly, oh, hey, Professor Garcia, what's the formula for the midpoint? I'd be like, I don't know, give me a moment. I'm going to redraw it because I literally cannot remember off the top of my head. I've never been good at that. I know some people can, but I can't. Okay, so basically what's pretty cool is if you want to do your approximation, your midpoint approximation, it's going to work very much like what we did before. You're going to have a sum where I goes from 1 to n, but now you're going to have f of mi times delta x. Again, I'm going to go through an example and show you in Wolfram about how to do this. And what's going to be sort of annoying about it is that you notice that mi is written in terms of what? The xi's. So to do the midpoint approximation, you're going to have to come up with your formula for the left and right endpoints, and then you'll use those to come up with a formula for your midpoints, which will then be plugged into your function. So in Wolfram, you're going to have f of x, or f of mi, but your mi is going to be written in terms of this stuff over here, right? So there is a lot going on. So we'll do a whole example. So hopefully that will make sense to everyone. Okay. So, but what I'm pointing out here is that you're still going to have a sum of f of something times delta x, just like what you did before. Just there's more junk involved, which makes it easy to lose track of it. I saw the laugh in the no shortcuts. Yeah, no shortcuts basically, right? If you want to do it right, there's a bunch of steps, which is why people hate doing this. Does that make sense? Because you sort of get to your if you try to skip steps and calculate something in your head, you're probably gonna screw it up, and then when you plug it in, it's gonna Wolfram's gonna spit out some stupid answer, or you'll have messed up your variables. So you have to do it in a structured way, always in the same order, I'd say. Okay, so let's do an example. So example, let's use the midpoint estimation with n equals 4 for the definite interval. Okay, and then, oops, sorry, let's scroll down. There we go. Okay, then my definite integral is going to be the integral from 0 to 1 of x squared dx. So we're starting off with some really easy examples, right? So you're like, okay, cool. My a equals 0, my b equals 1, which means my delta x is going to be equal to b minus a over n, which is 1 minus 0 over 4. You get 1/4. You're like, okay, cool. Delta x is 1/4. Easy. Not that hard. Okay. Now, yeah. We'll get into the harder ones eventually, don't worry. I mean, but they all follow the same thing, interestingly enough. Like, if you can do an easy one, if you just keep your mind, like, plugged in, screwed on right, like, it works the same. It's just, you're going to change what n is. Okay, so now you find the xi. Well, your xi is a plus delta xi. Your a is 0. Your delta x is 1/4, so you get I over 4. So what's your xi? Just I over 4. And I'm going to do it in different colors so you can see like the different work, right? Okay, now here's the annoying thing. Your midpoint formula is in terms of your xi formula, correct? So your mi is going to be xi minus 1 plus xi over 2. Okay, xi minus 1 is literally I minus 1 over 4. What's your xi? I over 4. And what is that all going to be over? 2. Luckily, like, you can actually do this one by hand, right? I'm like doing a first easy one by hand to show you could do it by hand, and then I'm going to also show you, well, how would you plug this into Wolfram? Now, what will this become? It'll become I over 8 minus 1/8 plus I over 8, right? Do you see how I divided everything by 2, so the 4s became 8s, and then I broke up the fractions, which is going to give me what's I/8 plus I/8. I/4 minus 1/8 is your mi. Okay. The delta x is 1/4. Yeah. Okay, almost. Okay, this is the thing here. I'm going to draw the picture because I get what you're saying. Here's x0, here's x1, here's x2, here's x3, right? And here's x4. Okay, notice the first midpoint is right here. Now, how far is the second midpoint? It's each time delta x away, right? That's why you keep on having this I over 4, because you're each time going to add 1/4. Now, where do you start? Half of the way to xi, which is why you have that 1/8, because the first one was 1/4 away. Does that make sense? Yes. You're not adding half of delta x. You're starting at half of xi, x1, and then adding delta x each time. Yeah. Okay. So, now you can set up your Riemann sum. You're going to do the sum of your 4 rectangles, so I equals 1 to 4. And you need to do f of mi times delta x. And then now you have to just start plugging junk in. Okay, mute yourself, whoever you are. I hear stuff in the background. So you have to start plugging everything in. Mi is I over 4 minus 1/8. And then what does f do to that? It squares it. And then what's your delta x? 1/4, right? Boom. So if you wanted to, you could just plug this sum into Wolfram and you would get something, or do it by hand. I don't want to do that. Does it make sense? Like, I'm going to say, at this point you could just plug it into Wolfram if you wanted to. But notice, we were actually able to calculate what mi was, right? We were actually able to calculate what delta x was. Okay, so now we're going to go see that Wolfram gives us exactly this. Why does it get squared? Because what does f of x do? F of x is x squared, so you have to take mi and square it, right? If f of x was sine, you'd take the sine of I over 4 minus 1/8. Yeah. Yeah, it's easy to forget that, right? Like your f of x was x squared from the beginning. Okay, so now we're going to switch over to Wolfram, and we're going to actually have Wolfram like do this for us. So let me change my window share. Oh, come on. I hate when I open a new window, it like doesn't show it. There we go. Like yeah. Oh, sure. Okay, you know how like they do weather forecasting? Okay, like to calculate. Okay, so ultimately, weather is the movement of particles, yes? So weather forecasting is literally looking at the heat in the ground, the shape of the ground, what you know about the content of the atmosphere, which includes the heat of the thing, the different sort of particles that are in there, and the amount of water. And ultimately, the sun's rays reflect from the ground. They heat the stuff. So much of it heats depending upon the properties of the thing. All that's calculated with an integral. Now what you do literally is like you break the world into little chunks like the size of like 500 feet by 500 feet, and you say like, well, in that 500 feet there, like you might as well imagine that like it's homogeneous. Like the heat is the same like in that 500 foot square. Does that make sense? Like, you know how like as you move through the atmosphere, the temperature will change? So you break it up into a partition, literally. You partition the atmosphere into like 500 foot chunks. And then if you want to figure out the effect of the sun's rays in terms of what that does to the weather, that's an integral. And then boom, like you do this. Like that's literally what supercomputers do like all day long. I mean, so what actually happens is they try to do like 3-day forecasts. Like they want to see what's going to happen 3 days from now, but it usually takes like a day to compute that, so it becomes a 2-day forecast. Does that make sense? Like if the forecast for tomorrow, you start calculating today, so that you could say tomorrow in 2 days it will be this, right? Like because there's like a lag there, and like that's just like they do all sorts of stuff like this with like if you want to look at how a part works. You can imagine breaking up some machine into a bunch of little squares, discrete squares, partition it, and you want to figure out like, well, when you put energy on it or start rotating it, what happens? Like in an engine, like a piston's going up and down, right? You want to figure out the friction as the piston moves, what that does to the deformation of the metal, right? Because like the first steam engines, they would blow up because there was like too much friction, right? That's actually why they invented all this stuff, to sort of figure out like, you know, what shape does things needs to be, like can it only go so fast before it will explode, like all sorts of crap like that. So it gets used all over the place basically. I mean, they use it for basically simulating anything. It's really about simulating. A forecast is a simulation, right? So whenever you want to simulate something, you're probably going to have to do some sort of integral, because there's some sort of influence that's integrating some function. Whenever there's an influence happening, you integrate that influence at any given moment, and it tells you after a certain amount of time what the net effect of that influence is. That's literally what integration is. Yeah, no, it is pretty cool. Once I started actually looking at it that way, I was like, oh, I see why like people actually give a shit about all this. Like, yeah, no problem. All right, so let's do this. So what's your f of x? Your f of x is x squared. Boom. Then you got to calculate your delta x. Your delta x is going to be b minus a, which was 1 minus 0 over n, right? Okay, and then your xi is going to be a, which was 0, plus delta x times I. And like if you literally say, hey, what's xi? Boom, it gives you I over n. And then what you could do is like replace n with 4, right? And you see how you get I over 4. Okay. Now you need your midpoint. Your mi is defined to be what? Xi minus 1 minus xi. Okay, wow, I just cannot type today. Divided by 2. So if you type in... Oh, shit, thank you. So if you type in your mi, what do you get? Boom, this. And if you go back and look at your notes... Oh, okay, and then let's replace the n with 4. So if you look at this... well, okay, we need to simplify it. We should get literally... This is what we got, right? If you do 1/8 times minus 1, that's minus 1/8. 1/8 times 2i is I over 4, right? That literally is what we got. But isn't it pretty cool that Wolfram will just do it for you? Like, you tell it, here's the xi, then you're like, well, my mi is in terms of the xi. And then I noticed I left the n there so that in case I wanted to change the number of rectangles, I could change it later. So you do this little thing where it's like you can set n equal to 4, and then I told it to simplify it. That's exactly what I wanted. Okay, now, what are you going to have to plug your mi into to actually do your calculation? You need f of mi, right? And we can replace n with 4. And I guess we can even ask it to simplify it. So if you were to simplify f of mi, you would get that. Oh, and then what do we need to multiply mi by? It's not just f of mi. We need f of mi times what? Yeah, so do multiply by delta x. And then boom! That's what we want the sum of. Apparently we want the sum of 1 over 256 times 1 minus 2i squared. Now, what do you need to do? Well, you need to sum that, so we'll just have the computer sum that. So we're like, okay, cool, let's sum that f of mi times delta x. And then what will your I go between? It starts at what? I'll pause because I know people are like looking and writing. So if you look back at your sum, it's 1 to 4. Yeah. So for the midpoint, it always starts at 1 and ends at n. Boom. Damn. There it is. And then we can just like calculate, hey, what if I want to integrate, let's see how accurate it is. I want to integrate f of x from, what was it, 0 to 1? Is that what we were doing? The original problem? Yeah, okay, cool. And then let's turn that into a number. Cool. So the actual answer is 0.3333. With our 4 midpoint rectangles, how close were we? Actually pretty close. 0.328 is not that far off from 0.333, right? Like that's actually pretty good for 4 rectangles. Mm-hmm. You do dash greater than, and it turns into an arrow right away. So you basically draw an arrow, right? Like, and it's yeah. I know, like, usually when people look at it, they're like, I don't see no arrow key on my keyboard, bro. And it's like, no, you just type it in and it will fix it for you. And now here's the cool thing, like how I did this. I can go and change the n value, right? Like if I wanted to, I could say, hey, let's see what happens if I do 10 rectangles. And then I would go from 1 to 10. And then, like, look, it's actually pretty accurate. Like, 10 rectangles gives you 0.3325. Okay, but there was a question? Mm-hmm. Yeah, dash greater than. Or dash greater than, yeah. Mm-hmm. And then after you press space, it should turn into an arrow automatically. Okay. Okay, so this is basically how it goes down. If you're going to do the midpoint rule, what are you going to do? You set up your f of x. Set up your delta x. Preferably leave n. Then do your xi. Then set up your mi in terms of xi. Then what do? Set up your formula for f of mi times delta x, just make sure that it actually calculates. Then just take that formula, put it into the sum, do slash dot n arrow, whatever, how many n's you want, so that because for a lot of the problems, like they'll say, remember like for the estimation problems, it was like do it for 5, do it for 10, do it for 50. You don't want to have to retype the same thing every time, which is why you should leave n and replace it later. The slash dot literally is telling Wolfram, hey, take whatever you had here, and I know there's n's in there, I want you to replace them all with 4 before you calculate anything. It's called the substitution rule. Like, does that make sense? It tells Wolfram to substitute n equals 4 before it calculates anything. Then what do? You have your sum go from 1 to whatever you replaced n with. So if it asked you to do it for 38 rectangles, you would just go and replace the 2 38s right there, rerun everything, and you're like, oh man, that's like pretty freaking accurate. It's like almost exactly what we want, right? It's accurate up to the 4th decimal place, basically. Okay? So there you go. Boom.